Welcome back to the Marsh Machine. Today on Marshable Math, we're going to be discussing inverse functions. So, get yourself some paper, some pencils, some graphing paper even, and let's begin. Now, if you're thinking inverse functions, maybe you've heard of the word inverse before. Inverse means like the opposite or backwards or something along those lines. And you've seen inverse elsewhere. We have inverse operations. For example, if I said 5 plus 3 and I add 3 to it, what's the inverse operation of plus 3? Well, you say it will be minus 3. And so if I take 5 plus 3 minus 3, I would get out the original thing that I started with. Well, hey, that just leaves you with 5. Add 3, subtract 3 is the opposite. Subtract 3 is the inverse. We've seen it before in terms of multiplication. If I said 6 times 5, and I said, well, how do I undo multiplying by 5? Well, you would divide by 5. And so if I take 6 times 5, and then I do the inverse operation and divide by 5, well, what do I get back out? Well, I just get back out 6, because those two cancel. You've seen it even with exponents, right? If I said I've got, oh, hang on here, I got x squared. How do I undo a square? What's the inverse operation of a square? Well, that would be the square root. Okay, and what do I get out? Well, I just get out x. Okay. So now what we need to think about is, what about an inverse function? Inverse functions are functions that will do the inverse or the opposite of what the first function does. Now remember that a function is a relation in which there is only one output for each input. Okay? And so let's take, for example, what did I use before as a metaphor for a function? The vending machine, right? You go to the vending machine and you press the button and you expect to get the same thing out every time. And so you go to the vending machine and you're looking for your favorite drink, the ambrosia, right? The nectar of the gods, which of course is Dr. Pepper. And in your urgency and haste and anticipation, you mistakenly press the wrong button. And you get out Diet Dr. Pepper. Now I admit, if I were to drink a diet soda pop, which I wouldn't do, but if I would, hypothetically, drink a diet soda pop, it would be a diet Dr. Pepper. But I don't drink diet soda pop because I don't like eat fake food or like drink fake pop or something like that. If it's going to be a soda pop, it's got to be a Dr. Pepper. So you're standing there going, oh my goodness, I didn't want this. What am I going to do? I made a mistake. Well, you would go over then to your inverse vending machine, and instead of putting money in the slot and getting out your Dr. Pepper down here, you would put the Dr. Pepper in the slot, and then it would give you out your money, right? Because I pressed the button, I did the input, and I expected to get the output, but it wasn't what I wanted. I got an output, but I want to reverse the process, right? So you would step over to the next vending machine, like, oh, I'm going to put this in, and you would get your input originally back out, right? That's what a function does. I'm not so sure that that would work in terms of a vending machine, but it's an interesting idea. So what a function does is a function would undo, an inverse function will undo what the first function does. So let's talk about an example now. Let's say that I had a function f of x, the ubiquitous name for a function, and let's say it's 2x plus 7. And I said, well, what if my input then was negative 3? What is f of negative 3? Well, that would be equal to 2 times negative 3 plus 7. And so then what is the output? F of negative 3 is equal to negative 6 plus 7. Is that not 1? Right? So what I've got here is this. I've got an input of negative 3, and I've got an output of 1. What I want to do is I want to find a function that reverses that process. Here's what I want. I want a function, let's just call it g of x for right now. I want a function that will do this. I want a function where I take my output and I put it in this new one as an input. The input comes over here as 1. And I want it to give me the original input out. So I want a negative 3. Do you think you can come up with a function that if you put in a 1 would give you as an output a negative 3? You think you could do that? It's probably not all that hard. But here's the thing. It's got to work for every single input-output function that you get from f. That's a little tricky. I can maybe come up with 10 different ones that would do that for me. But it has to work for every single input-output pair that you get from f. And that's the challenge. There's a little step-by-step process by which we can figure it out, though. What's really going on is we're doing this. We're switching the domains and the ranges, right? The domain is the allowable inputs. The range is the allowable outputs. Usually we call those x's and y's. We're switching the x's and y's around. So what if we do that with the equation itself? Here's a little checklist. What I'm going to do is this. I'm going to take the original function f of x, and I'm just going to replace f of x with y. I'll go back to the old style of doing it. I'll say y is equal to 2x plus 7. Okay? And now here's what I want. I want my x and my y's to exchange places. So I'm going to leave all the other stuff there and just swap the x's and the y's positions. Wherever I see a y, I'm going to replace it with an x, and wherever I see an x, I'm going to replace it with a y. So the next step down, because these are not equal to each other in a sense, the next step down would say, hey, this becomes x is equal to 2y plus 7, right? This is now the beginnings of the inverse function, because what we're doing is we're switching the inputs and the outputs. We're switching the x's and the y's. We're switching the domains and the ranges. Now if I can solve this equation for y, I would then have what I want. So how would I solve this equation for y? Well, I would subtract 7 from both sides. So the next line down becomes x minus 7 is equal to 2y. And then I would divide both sides by 2. And so I would get this in the end. I would get y is equal to x minus 7, all of it divided by 2. But again, we don't want to call it y. We want to call it something that in function notation, but we want to call it something that references the original, right? Because it is an inverse. These two are related to each other. So if f of x is the original function, inverse would be f to the negative 1 of x. Now you've seen the negative 1 before perhaps as an exponent when I said something like, hey, 3 to the negative 1, that's equal to 1 over 3. You know the negative exponent means to take the reciprocal of the base and so forth. But this is the multiplicative inverse. It has to do with when you're multiplying things, right? So instead of multiplying, we're dividing. This is the inverse function. It doesn't mean we flip it. It just means it's the inverse again. But this time it's a function. So let's try it. Let's try this. Let's see if I can do f inverse of, I want my input here to be my old output. So that would be 1. And I want to see if what I get in the end is actually negative 3. So let's try this. 1 minus 7 all over 2. What is 1 minus 7? Is that not negative 6 divided by 2? And voila, negative 3. Okay, there you go. Here's the pattern if you want to write it down. Number 1, replace f of x with y. Okay. Write this down probably. Replace f of x with y. Then you're going to switch your x's and your y's. Every time you see an x, you write a y, and every time you see a y, you write an x. Then you're going to solve the equation for y, and you get an expression over here. Okay? And then the last step is to replace the y with the inverse symbology here, the inverse, the notation if you want to call it that. And then that's your inverse function. And if you think about it, this really kind of makes sense, because look, what we're doing here is this. What do I do with my input? Well, I multiply it by 2, and then I add 7 to it. What's the opposite process? Well, I'm going to subtract 7 from it, and then I'm going to divide it by 2. Okay, does that make sense? Let's try it with another pair and see if it works, because remember, it has to work with every single x and y combination. Let's do, let me pick a positive number this time. Let's pick f of, oh, I'm making this up, 4. F of 4. So that's equal to 2 times 4 plus 7. Let's see if I can do basic math. 2 times 4 is 8 plus 7. Isn't f of 4 then equal to 15? 8 plus 7? 15? If this is my inverse function now, which is this one right here, I have to take then 15, run the process as an input, and then it gives me back 4. Let's try it. What is F inverse of the output here? 15. The output for the 1 becomes the input for the inverse. What is that? 15 minus 7 all over 2. What's 15 minus 7? Is that 8? 8 over 2. Woo-hoo! I get 4. So here's what's going on here is I am finding the function that will take my output as its input and give me my input back as an output. So I got to think about this. If I'm going to put my input in and I'm going to then get an output out, and then I put the output in and I get the input out. Hey, you know that? That actually reminds me of a song. Hang on a minute. I love to sing. This is fun. So hang on here. You put your input in and you get your output out. You put your output in and you get your input out. You do the inverse function and it turns the math around. That's what it's all about. Yeah, that's it. Did you get that one? Yeah. Maybe you've heard the tune before? Yeah? Sing along. Especially if you're in public. Sing along. It will weird people out. But you're having a good time, so yeah, it's all good. Okay, let's go. You put your input in, you get your output out. You put your input in and you get your input out. You do the inverse function and it turns the math around. That's what it's all about. You put your input in, you get your output out. You put your output in and you get your input out. You do the inverse function and it turns the math around. That's what it's all about. And that's what it's all about. That's what I'm talking about. Yeah. Wasn't that satisfying? Yeah, that was good, yeah. Hold on. All right, back to normal. Try this. Let me give you a practice one to do. Practice one. Let's call this one h of x. H of x, I'm going to say, is 5 minus x all over 3. Okay? I want you to find the inverse function. Go through that process I gave you and see if you can come up with the inverse function. Go. Press pause. Do it to it. Put your input in, you get your output out. You put your output in and you get your input out. You do the inverse function and you turn the math around. That's what I'm talking about. Hope you're done. Okay, here's what we do. Again, replace the function notation with y. Y is equal to 5 minus x all over 3. Why? Well, because that's how we do it. Now, I'm going to switch x's and y's, so a little break here because it's not the same thing. So this becomes an x minus, equals 5 minus y all over 3. Solve it for y. I would multiply both sides of the equation by 3. This gives me 3x is equal to 5 minus y. Oh no, there's a negative involved. Let's see here. Subtract 5 from each side, so I'm going to get 3x minus 5 is equal to negative y. Multiply everything through by a negative, and then spin the thing around because I like my variable I'm solving for on the left. Does that not become y is equal to 5 minus 3x, or maybe 3x plus 5? Am I good? Oh, one more thing. I got to call this h prime of, or not h prime, h inverse of x is equal to 5 minus 3x. So I'm going to say this here is equal to 5 minus 3x. And so now I have a question. All right, so this is my original. This is now my inverse. Let's try it with an actual value. Let's take a risk here. Let's try h of 11. Okay, if I do h of 11, it becomes 5 minus 11 all over 3. H of 11, 5 minus 11, isn't that negative 6 all over 3? Okay, that's equal to negative 2 if I've done the work right. So this is the in, this is the out. Now what I have to do is I have to take that out and I have to put it in my inverse function. So the inverse function would be h inverse of negative 2. So that's equal to the inverse function 5 minus 3 times a negative 2. Oh my goodness. 5 plus 6. Holy moly. 11. H of negative 2 is equal to 11. Did it work? I think so. Try it with something else. It should work for every single input-output pair. Okay? So again, what we're doing with an inverse function is we're switching the domain and the range. We're undoing what the first function does. We're switching our x's and y's. Well, if we're switching our x's and y's, we can actually do it on a graph. We don't actually have to have the equation. Well, first let's do this. Let's pretend we just had some ordered pairs. If I just gave a function that was nothing more than just some ordered pairs. So let's see here. Let's call it k of x. Hey, k of x is just some function that produces 5 and 3, and then it also produces a 6 and a 2, and then it also produces a negative 4 and a 12. What does the inverse function produce? Well, all we're going to do is just swap the domains and ranges. This point would be 3, 5. It is switch, right? This point would be, hey, the input's 2, whoops, dang it. The input's 2, the output is 6. This one says the input is 12, the output's negative 4, okay? Because all you're doing is switching them. So if this is what we're doing with the table of values or with ordered pairs, then we can definitely do it with a graph. So if I have the graph of a function, which I will draw here in green, and let's see, I'll just do a line because a line will be the easiest one to do. Let's say that I've got this function right there. And so I've got a line that comes through here like this. And you're looking at the graph and you're thinking, wow, I'd like to find the inverse function of that one right there, but I really don't know what the equation is. You can probably figure it out. It's kind of a simple one, right? It's a linear equation, y is equal to mx plus b. But how do you do it with just a graph? Well, I need to go through and I need to find points. Well, let me pick some point here. This is obviously the point 0, 3. This is the point 1, 2, and then up 1, 2, 3, 4, 5, 6, 7. This is the point 2, 7. Well, let me switch those now, and that will give me points on the inverse function. So instead of 0, 3, it's 3, 0. And instead of 2, 7, it's 7, 4, 5, 6, 7, 2. It's this right here. And if I did it with every single point, they would all map out the same way. And so what I get then is I get this thing, like this. Notice that they are going to intersect down here. They don't always have to, but they will intersect somewhere down here. There's going to be one point that will solve the original and the inverse. But notice there's a symmetry to that. There's something more going on here. If you'll notice on the graph, these points are a reflection about the line y is equal to x. All we're doing, since we're switching x's and y's, this is a reflection around this line. Now, this blue line I'm drawing right here is just for illustration purposes only. It's not actually part of the inverse. But you can see that the green has a reflection about that one. And so what do you do if they're not just a straight line? Well, you do the same thing that you would before, and that is you reflect them about the line y is equal to x. So for example, and this is going to really test my artistic abilities here. But if I had something that looked like, I don't know, maybe like that, what does that look like? Well, I'm going to go through here and find points. It looks like it's this one here, and it looks like it's that one there, and then it curls around to maybe this one here. So this is 0, 2. So I know that 2, 0, this one right here, is on the inverse. What is this one? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. So that one's 3, 7. So I want 7. I want that point right there. And then this one goes over 2 more, so then that one's 5. And then up 1, 2, 3 more, that's 10. I don't know if I have room on this graph here. So then it goes 10. And then 1, 2, 3, 4, 5, something like that. And so what I get is this shape here comes in, comes around. Am I doing it right? It should be, I feel like I'm missing it here. It comes, 3, 7. Did I do that one right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. Yeah, I'm not feeling it though. Does it come in more? Oh, it comes in more. It comes in more and then it comes up. And then around like that. Oh man. Whew, it's like a base. Okay, it's kind of pretty though. I like symmetry. Yeah, life. It's good when life has symmetry. So it's symmetric about the line y is equal to x. So if you just need to transfer some points around, you should be able to do it with just the graph. Okay. Let's see. What else? Oh, one more thing. 2 more things. Do you remember when I was doing just like the +3 and the -3 and the multiply by 5 and the divide by 5 and then even the square and the square root? Did you notice that those things gave me back my original? Right? That's true of functions. If you do a composition of inverses, you get the same thing. So let's go back. Let's see if I can do this correctly. We had, let's do f of x. F of x was equal to 2x plus 7. And what was f inverse? F inverse is equal to, write it down. I don't have to do it again on the board. What if I make a mistake? That happens from time to time. I have to shoot the whole video over again. I think it was, we're going to multiply by 2 and then subtract 7. It would be the x plus 7 and then divided by 2. If I do their composition, if I do f of f inverse of x, I should get out just my original value. So if I took f of x, or the inverse, and put it inside the original function, and I simplify it, I should just get x. So let's see this here. This is going to be 2 times a something plus 7. And what am I going to put in? I'm going to put in x plus 7 divided by 2, and I'm going to simplify that. No, I missed it. I missed something here. Oh, is it a negative? It's a negative. Negative? Negative. Multiply by 2, add 7, then I'm going to subtract 7, and then divide by 2. There we go. Okay. So now, if I simplify this, notice that the 2's cancel, and I'm going to get x minus 7, then plus 7, and when I simplify that, I just get out x. Okay. That's a way to guarantee or to confirm algebraically or analytically that you've got the inverse. Now, not all functions have inverses. There are some things that you do that you aren't able to kind of undo. All right? And if you remember, if something was a function, it was able to pass a vertical line test. So if I had a quadratic here like this, is that a function? Well, yeah, because I can take a vertical line and pass it anywhere along here. And because I only have one output for each input, I don't have 2 y values that have the same x values. So if I pass this vertical line through here, this is a function. How do you tell if something has an inverse? It has an inverse if it passes a horizontal line test. So can I pass a horizontal line test through here and have some place where I have the same y value but with 2 different x values? Does it touch the graph in more than one place horizontally. In this case, yes. So a parabolic function doesn't really have an inverse function. Why is that? Well, because when you switch them around, you actually do get two outputs for the same input, and that's not allowed. Okay? So a way to test to see if something actually has an inverse or not, if you have the graph, is to try the horizontal line test. Okay? I think that's it. Did you enjoy singing today? I know I did. Hope you have a great day. Hope you learned something. Talk to you later. Put your input in, get your output out, you put your input in.